Welcome to MLOps Live, a podcast by Neptune.ai.
We host in-depth discussions where machine learning practitioners answer questions from other practitioners about one subject related to production machine learning and MLOps.
Tune in to get real-life stories, dirty hacks, and pragmatic workarounds from ML people in the trenches. Hey everyone, welcome back to MLOps Live. I'm Sabine, your host, joined by my co-host Steven, as always.
Hi everyone. Hi Sabine.
Hey, and our topic today is implementing vector search, AMA, and the subject of the AMA is, of course, our guest, Kacper Lukawski. Welcome, Kacper.
Hi, I'm very glad to be here. Thanks a lot for the invitation.
We're glad to have you. So, Kacper, you are a developer advocate at Quadrant. Is that right?
Yeah, exactly. I joined the company in May 2022, so I'm kind of new in the world of vector search, but during the last month, hopefully I got some knowledge that will be important to answer all your questions today.
Oh, I'm sure. So it's an open source vector similarity search engine, right?
Yeah, exactly. We also call it vector database. That is also quite a popular term.
Yeah, we'll be delving into that soon enough. And you have actually a background in informatics, but then you got more into data science. You've been a data science lead at Codete, and you're also the founder and chairman of AI Embassy, which is an NGO focused on spreading AI knowledge. So I'd just be curious to know a little bit how you started moving from informatics into data science and AI.
Well, that was like a natural transition, I would say. I think that many people did exactly the same process because everything actually started with software engineering. I joined Codete, and that was the company that was also interested in doing something more in data science. There wasn't even a term of data science back in the days when I joined. And there were some customers who really wanted to implement this kind of solutions. So that was like a natural transition. We had the same opinion of how the company should grow and what should be the direction. So that came pretty naturally. But I'm really glad I had this chance because that's really amazing and exciting career.
For sure. All right, we'll be getting into all the questions very soon. Before that, just a reminder that this is an interactive Q&A session. So if you're here, all you need to do is raise your hand here in Zoom. We will unmute you and you can just go ahead and ask your question from Kacper. You can also type in chat if you prefer. Don't worry if we don't take the question right away. We do store it and we'll pick it up as soon as possible. And this recording will, of course, be released as a podcast later on, so you can catch up with it in a couple of weeks once it's released. All right, so Kacper, to warm you up, how would you explain MLOps for vector search in just 1 minute?
Well, so MLOps for vector search is not that different comparing to MLOps. It's just a different way of how we use neural networks. Because basically, if we want to start doing vector search for any kind of problem, that's quite a universal tool. We typically need to make a decision of what vector database we want to choose, just because this is just another service that we need to have in order to do that efficiently. But other than that, there are challenges that all the MLOps engineers should already know, things like how to deploy an existing model. There is not a huge difference. So I would say vector search shouldn't be a challenge for an experienced MLOps engineers. There is only one additional piece if you are ready to do any kind of data modeling.
Awesome. That was pretty much exactly 1 minute. So cool. Nice job. Then we're ready to head into the questions.
Great. Nice once again to meet you, Kacper. I think one thing that will be sort of useful, sort of setting the tone for the particular episode, is to really understand the applications where, you work with Quadrant. So obviously, what are those applications you see vector search being really, really useful in? And let's use that to spiral into the episode.
Yeah, sure. So first of all, people try to replace those old, pretty well-known methods like BM25, which is quite commonly used for keyword-based search. And people try to replace them with vector search just because those modern vector-based methods do not require that much effort in terms of configuring all the stuff. Let's say if you were doing some e-commerce search for your store, you would typically need to hire a team that would be configuring the Elasticsearch or OpenSearch stack for you. So that will be capturing more and more queries that will be sent to your users. But vector search is not only about performing search in terms of keyword-based search, but it's also a tool that might be used for classification, anomaly detection, and many other challenges that we have solved with machine learning so far. That's just a different approach based on similarity. And surprisingly, everybody who has any kind of experience with machine learning has already heard about algorithms that are being used, because KNN, K-nearest neighbors, is probably one of the easiest algorithms, and that is taught on primer data science classes. And that is actually, in a nutshell, the process that is being done by all those vector databases. They truly rely on KNN approximation methods to make it scalable. So basically, vector search is quite universal, and people try to solve traditional search or information retrieval, but also image similarity or semantic search or anomaly detection as well. But various applications I probably haven't heard of.
Right. That makes sense. And we had a particular episode, right? And this was like a few episodes ago, I think around June or something, where we talked about neural search and really dig deeper into that particular part of information retrieval. I'm sort of wondering, why should teams consider choosing vector search over such type of like other information or generally other information retrieval techniques like neural search or maybe traditional techniques and stuff?
Well, basically, the good thing about vector search or neural search, because those might be treated as synonyms more or less, the main difference is that those neural models are already able to capture the semantic of the documents. So this is pretty useful. With those old methods, you had to provide, let's say, a list of synonyms in order to support different words being used in the query. With neural models, it's no longer the case, because those deep language models are already capable of handling the synonyms, but also some other things like typos and issues that may arise when you try to implement the keyword-based search. So that's cool. That doesn't require lots of effort in order to implement those cool additions to the traditional search. But I wouldn't say it's like a one-to-one replacement. Definitely, if you feel fine with your keyword-based search, let's say you implement a system that is being used by some domain experts, let's say by the doctors, they would typically know the terminology being used in that specific area. But from my personal experience, when I was still studying and I had to use the search system that was used by the library, that was a horrible experience, probably the most painful thing I encountered at my university, just because I had to know the exact words that were used in a particular book title or in the abstract describing it. With semantic search, with neural search or vector search, however we call it, it's no longer the case. And the search system might be used even by somebody who has no experience with that specific data set and that we perform the search on.
Right. And I think you mentioned a few applications earlier. And when I think of those applications, I'm thinking of the fact that when you're thinking about vector search, it's maybe not significantly different problem, but it's a different problem putting that into production, right? Because you're dealing with maybe large number of embeddings, data sets, and so forth. And I'm sort of wondering, what are some of those components you need to keep in mind when implementing like MLOps for vector search applications?
Yeah, sure. So basically, first of all, you need to have a model. This model should be capable of converting your data, whatever you work with. It might be text, images, videos, or actually any type of data you can imagine. That's pretty universal. As long as you are able to design a network which will take this data and convert it into the vector representation of a fixed dimensionality. So you need to have a model, and that model should be deployed somehow. But this is the challenge that MLOps engineers are already solving on their daily basis. So I wouldn't say it's a huge problem. There are already some tools that simplify deploying those models and scaling them up on demand. But there is also another component that you need to think of if you want to do it on a bigger scale. Historically, there were some libraries allowing you to, let's say, experiment with vector search on your machine. You had to use lots of memory in order to support that. But basically, that was like using pandas for experimenting with your data. But if you want to move your code from the notebooks into the production, you also typically need to change the tool you are using to transform the data. And the same is true for vector search. You have the model, but you also need to switch from the vector search library, things like FICE or Annoy, which are intended to be working on a single machine. But if you want to scale it up, you need to switch to a fully fledged vector database like Quadrant, for example, that will allow you to store all your embeddings and spread them across a cluster in a distributed mode. So those vector databases will typically allow you to search for the nearest points in that vector space, but also to manage multiple collections at once. There are like CRUD operations that you typically want to perform on those embeddings as well. And this is already built in. But the greatest thing about those vector databases is the fact that you can actually launch it on a bigger scale, and you don't really need to rely on a single machine, single point of failure with hundreds of gigabytes of RAM. That was the biggest challenge with vector search back in the days. They were thought to require lots of RAM to work well.
Right. And for the MLOps part, you mentioned these are like day-to-day challenges they're already facing. Or can you sort of give us a scenario where these models or maybe like pipelines or stuff are actually being managed in prod, and how maybe some teams are doing theirs? Because I assume that might be slightly different, especially when you're talking about these databases, for example. These are like slightly different challenges, how do teams sort of manage these things in production?
Yeah, sure. So those models may be actually launched however you did that before for any different challenges. But in terms of vector databases, things are of course different depending on which vendor you choose. But most of the vector databases are open source and they are quite well documented. Most of them, including Quadrant, will allow you to spin up the cluster using Kubernetes or even use a cloud version of them. So things are not that complicated, and the configuration is not a big deal. This is like a tool which is specifically designed to solve this one problem. So the configuration is not an issue, and the distributed mode of those tools is typically already built in. I'm not sure about all of the existing open source tools, but most of them will be rather easy in terms of management.
Right. And we are definitely going to be circling back to some of those components later on in the episode. So I just want to jump right into some of the community questions we're able to gather. And the first question here is, this person asked, what are the advantages and disadvantages of vector search? Is it something that you want to?
Yeah, there are a lot of challenges still. It's a relatively new approach, I have to say. But what are the advantages? Some of them I have already mentioned, but basically this ability of neural networks to capture not only the words being used in a document, but also the concept, the semantic meaning of the words. So that's a huge advantage over those traditional search methods, but not only. And the huge advantage is also the availability of some pre-trained models. So back in the days, if you wanted to actually solve any kind of problem with machine learning, you had to design a model, train it from scratch, and then apply it for your data. This is not true in terms of vector search. There are already some existing pre-trained models that you can use out of the box when it comes to textual search. If you work with any, let's say, popular language, you can probably go to Hugging Face datasets, choose whatever model works best with your domain, and then use the predictions out of the box. So actually you skip the problem of training the model, at least training from scratch. Sometimes you just need to fine tune it. And that's the disadvantage. That's also an advantage and disadvantage. There are some pre-trained models that you can just take out of the shelf and use as provided. But if you work in a specific domain, let's say in medicine, the terminology that is typically being used would be different comparing to the general language. Those huge models like BERT-based models are typically trained on Wikipedia and some book corpuses from Google. But if you work in a specific domain, let's say you want to implement a chatbot, the question answering for a specific company that works, let's say in the transport area, then there might be an issue. There would be a different terminology being used by your users, and you need to fine tune those models. And that's the challenge for somebody who is not really into training the models and serving them somehow. So that may be one of the disadvantages of vector search. The other one is the way of how we are going to update the models, because the requirements change. We conduct some experiments, we fine tune our models further and further. So at some point of time, we will definitely need to tackle a problem of updating the embedding that we already have. Vector databases are typically just storing the embeddings. So every single time we change the model, we also need to recompute all the embeddings for all the data that we have in our collection and somehow switch to the new version of the model, because that has to be done somehow. So that's one of the disadvantages. That might be a huge effort to do it efficiently. And there are various components that has to be updated in the same time.
All right, nice. I think we have a question in the chat, Sabine.
Yeah, we do. And this is really going into those vector embeddings. So we have Girish Sai asking, which one would you recommend for finding the similar vector embeddings, cosine similarity or dot product?
I would say it doesn't really matter depending on how you train the network, because cosine is probably the first choice. I would say like 90% of our users use cosine similarity to compare the distance, but some of them also use dot product. I know that dot product is quite commonly used if you design a recommendation system based on two-tower models. But at the end of the day, there shouldn't be huge difference that has to be tested. That's the answer. That really depends.
Right. So you might need to feel your way forward a little bit.
Exactly. Depending on the problem you try to solve, that might be a different, or if you have some pre-computed embeddings, maybe they were trained to minimize the cosine similarity or dot product. So that might be also that difference.
All right. Thanks for the answer. And thanks, Girish, for the question.
Great. I think we can jump right into our next community question. And this person asked, does vector search scale well in production? Thoughts?
Yeah, it does. It actually started scaling well like a year or 2 years ago, because before that time, there were no vector databases designed specifically to tackle that. So the only thing that we could do was to build our own system around that. And those big players definitely did that because, Google uses vector search quite extensively. It's part of the Google search right now. I think that they switched to BERT encodings for majority of languages. So that happened, but for smaller and medium-sized companies, there was a revolution of vector databases, and there are various startups around the technology. So I have to say that was a challenge that is already solved, and if you just choose a proper tool, you will be able to simply scale it up, run it in a distributed mode, set up a cluster using Kubernetes, for example, and that shouldn't be a huge problem, even if you have millions or billion scale vectors.
All right. I think that's a fair answer. Hopefully that's a fair answer for the person. Maybe not quite sure, but yeah. Again, I think we are in the MLOps community. So if you don't have a satisfactory answer, you can always reach out to Kacper in the community as well and other places online. But yeah, this next question, this person asked, in what use cases does vector search work the best compared to other search techniques like keyword search and stuff?
Well, if you want to have exact matching search, for example, you are looking for a specific phrase and words do matter, then probably keyword-based search is a better choice, just because it will capture exactly those words that have been used in a query. But for all the cases where your users are not experienced in terms of the data you have collected, and if you want to support, let's say, multilingual search, that's something that actually cannot be efficiently solved with keyword-based search. Let's say you wanted to implement a search for a specific store and you wanted to support 10 different languages. So if you wanted to do that with keyword-based search, then you would need to have like a specific pipeline, specific database for every single language, or at least translate all the text into all the languages you want to support. Well, there are various ways of how to solve that, but basically that would be a huge problem to do that. But with properly trained neural network, you are able to convert text in various languages into the same vector space. So effectively, you are getting a tool that simplifies that process. So that's not something that could be easily solved with keyword-based search at all. But also things like semantic search has been already mentioned, of course. If the words are not that important, you care about the meaning of the query, then keyword-based search will struggle with that. But also keyword-based search is limited to texts. If you want your users to provide a query and search for not only the textual description of the items you sell, but also to the content of the images, the thumbnails you provide to your products, then that's also not solvable with keyword-based search unless you provide a textual description to every single image. With multimodal vector search, that's also doable. You can convert images and text to the same latent space and perform the search either using images or text. And yeah, I would say that's it. There are some cases where keyword-based search would work perfectly fine, but some of the challenges have not been solved for ages with that approach. And vector search is a great alternative that allows to do it quite quickly.
Yeah, and the final question from this community member, how can they get started in vector search right now? The libraries, tutorials, stuff?
Yeah, sure. So basically, there are a lot of tutorials on our website, some of them also written by me. So if we can just put some links into the description, I can also point to some great articles describing how to start with that. But there are also various ways of how to do it if you just want to start. If you have no experience with designing the models or fine-tuning them, it's also not required. Even last week, Cohere and OpenAI have published their APIs that allow to take embeddings through HTTP APIs. So you don't really need to handle the model training part. You can just use some existing APIs in order to retrieve those embeddings. And then the only thing that you need to care of is how you are going to perform the search. And I would strongly encourage you to have a look at the existing vector databases. Of course, Quadrant is the option that I would really suggest having a look at. But if you just want to experiment, there are also some tools that you can use directly on your machine. Those vector databases are rather designed to support production load. So for experiments, those libraries are also fine enough. But if we are talking about production system, then choosing the right vector database is an important step, and that is required to handle the load that may occur.
We have a community question in the chat. We have Pablo who wants to know a bit more about memmap storage. So he's asking, working with billions of vectors can be too expensive if all vectors are stored in RAM. Could you explain how memmap storage works? Is the latency of the search significantly affected?
Yeah, of course. Maybe for those who do not understand the question, it was thought that vector search requires a lot of memory to work properly. And that was true if we wanted to have really low latency. But there are also some cases when we don't really want to store everything in RAM, where we can store some parts of our data that is not being used right now. We can store that on our disks. And this is something that we have published recently with Quadrant. There is a way to put those vectors not in the memory, but also store them on disk and just access them through mmap on demand, so whenever they are required. That, of course, affects the latency. It will be significantly higher. And if we talk about billion search scale, I have no answer here. Unfortunately, we haven't benchmarked this memmap storage yet for that scale. But with several millions of vectors, that works pretty well, depending on how you set it up. If you really want to get to the maximum, we have benchmark. I think that was the benchmark done like 2 weeks ago. And we were able to run a system serving around 1 million of vectors using around 130 megabytes of RAM. So that's also feasible. Of course, the latency is extremely high in that setup. So we need to find a sweet spot of how much memory we can provide to that machine. Again, I would really love to put a link to the benchmark we did. There are a lot of experiments being conducted. So I think that's a great starting point to just see how much we can store on disk and how much memory we should provide to work well in a specific domain. But I would be happy to benchmark that. I'm not sure who asked that question, but please just feel free to reach me out. Would be happy to do this benchmark because that's also something that might be really interesting to know.
Yeah, so the question came from Pablo Vargas. So thanks, Pablo, for the question.
Thank you for the answer.
Yeah, if you have any links or resources to provide, Kacper, we can just share them later as well in the MLOps community Slack or through other channels that we agree on.
Perfect. So. I'll do that for sure.
All right, thanks.
Great, thanks, Kacper. Speaking of benchmark, we have one particular question, and I don't know if it's super clear or really relevant to this, but this person asks, what are your best practices and tools for benchmarking vector search engines? That's it.
Maybe there's one thing I should mention here, because there are some benchmarks that compare the speed of those engines, so how fast they are able to provide you some results. But for vector search, there is another thing that we need to keep in mind, and this is the precision of search. It's quite easy to provide any results within a fraction of a second, but if you really care about the precision of your search, you need to compare the other fixed precision threshold. So let's say I want 95% precision. What is the speed of every single vector database? And that's the proper way of how to design this kind of benchmark. And this is actually what we did when we were comparing ourselves to the other solutions. So this is one hint from me. And yeah, we also need to keep in mind that every single system has to be launched on a specific hardware. So comparing cloud-based tools with tools that we just locally launch using Docker or Docker Compose is not a proper test. That also required to freeze the hardware that is being used and see how much we can get from every single engine given those hardware constraints as well, including memory.
Yeah, that's super clear. And still on the matter of speed, do you have any effective methods for optimizing classifier training with vector search? I mean, speeding up the training process and all of that.
Well, the only thing that comes to my mind is I already mentioned those pre-trained models. So if you really want to perform the classification, maybe I just need to make it clear of how this classification is going to work. Because basically all those vector search engines will use some sort of approximate nearest neighbor search to provide you the results. So actually you can also build a classifier on top of that. That will be similar to KNN classification. So you would just choose, let's say, 50 closest points in that space. And by simple voting, you are going to select the most probable classes for your query. So there is a chance to build a classifier on top of that. But under the hood, we are just going to use some representation models producing those neural embeddings. So the piece of advice I can give is to just start with some pre-trained models and fine-tune them with some boundaries. There is Quaterion. This is the open source library, which was also created by us because we realized that there is an issue with fine-tuning those models for similarity learning or vector search. So we created a framework that provides you, this is PyTorch Lightning compatible. So if you use PyTorch or PyTorch Lightning, this is fairly easy to start working with. But that gives you a framework of how to fine-tune those models with just a little effort. Because the idea behind that is that we freeze this original neural encoder that you take from any hub, like Hugging Face datasets, for example, and just attach a new head layer. So you're just adjusting the original embeddings produced by those pre-trained models. And that's a great trick just because that enables to cache some of those original embeddings. They may be just computed once, and then the training takes like 100 times less time than it would take for the fine-tuning of the whole network. And that's a great trick. And for that setup, you don't necessarily need to provide like millions of examples, but since your pre-trained model is already capable of capturing some signals in your input data, you can just provide, let's say, 1,000 or 2,000 of well-labeled examples and then fine-tune. So those original embeddings will be just slightly adjusted from the original space, and they should ideally capture some more meaning of your documents. So that's basically how we can make it faster. But I would say let's focus on less data, but of a better quality. And if you agree to fine-tune your models with those boundaries, then you should be able to experiment quite quickly and train a few models a day without waiting a few days to see that what you have produced is just simply garbage.
Yeah, and are there any sort of notable trade-offs, when you're trying to optimize for speed? And then, what other trade-offs are you what are you trading off when optimizing for speed in that case?
The bottleneck of those systems is the model that you use. So you can use tricks that are already known for machine learning if you care for speed. I would say that if you want, you could try to reduce discretize the network. It will work with integers instead of floats of doubles, or reduce the type of data that you use. That are tricks that are quite commonly known. But I would say vector search is not the problem here, is how you train those networks. So probably the goal should be to start with the simplest available model. And then if it's working well enough, just stop experimenting with some more complex structures.
Okay. So the next question from Devin mentioned he has a large data set that he would love to, pre-compute and store embeddings for. How can he know how much he's going to lose by storing them as floats? Because obviously he's looking at, cutting storage costs and optimizing loading times. Yeah.
Yeah, it's related to the previous question, actually. So I would say there is no other way than just benchmarking that on your own. Probably that will be different depending on the domain you work with, the data set you used. But making this experiment and just selecting a subset of your data just to estimate the possible change on the quality of your embeddings is something that can be done quite easily. If you already have a model that is trained with float 32, switching to float 16 shouldn't be an issue, and testing the quality of your embeddings, the metrics that you really care about, is not an issue. But that's probably the only way I can imagine. But I agree that may be a challenge if you have to store like millions of vectors. Saving like half of the memory is a great way to reduce the cost of that sort of setup.
Right. Awesome. So another question from Matej in MLOps community. Do you have any experience with filtering on GCP vertex AI matching engine? How useful is that for vector search?
In this war, AWS versus GCP, I would probably go for AWS. So unfortunately, there is no experience with this solution. But when it comes to filtering in any kind of vector search, that's an important topic. And I assume the question is exactly about the topic I'm going to talk a bit more about. So basically, vector search is not the only thing that we need. Let's say we want to create a system for reverse image search, and we want to find a similar piece of cloth based on the image that we have. That's cool, but we not only care about the similarity of the items themselves. That's quite cool that we are able to find some similar pieces of cloth and buy them online, but we also care about fabric that has been used to produce it, or we want just a slightly different color. We like the pattern, but not necessarily the color that was used. So we need to apply some filters on top of vector search, because this similarity won't give that answer directly. So basically, this is the mechanism that's probably built in all the vector databases together with, so you can provide some sort of embedding to find some similar entries, but at the same time, you can also provide some additional criteria. I assume Google Vertex AI has exactly the same mechanism like every other system. So basically, this is actually already built in all the systems that I know. There are various ways of how to do that for quite a long time. There are two approaches like pre-filtering and post-filtering. So we are either filtering the matching items before the vector search or after the vector search. There have some different advantages and disadvantages, but there is also another way, like the one that we have in Quadrant, that is filters are applied during the vector search process. So you always retrieve that many relevant items as you wished, and also you only get those items that fulfill given criteria. I haven't played with Google Vertex AI, but I assume that's exactly the same mechanism. But this is quite important. If there was a different question about how to choose a proper tool, if you really care about some additional criteria, then having a look at what a specific vendor may offer here is also quite important, because that will be quite hard to extend that if it's not already built in.
Right. Good points. Sabine, I think we have a question in the chat.
Yeah, I'm not sure. Maybe this is what came up a little bit already, but Girish has a follow-up question. For recommendations, we are currently using Vertex matching engine for real-time similar vector inferences and for offline batch predictions. And he's saying we are considering to use SCAN, SCANN. Is there better alternatives to SCAN for offline batch inferences? That's his question.
I'm not really familiar with SCAN, I have to admit that. But basically, if you are already using a specific tool, then switching to a different one shouldn't be a problem. I would really encourage you to test some different options. There are also some benchmarks, depending on how much data you are going to work with, that might be a different answer. SCAN might be working fine in your case, but there are some benchmarks like annbenchmarks.com that should clarify which algorithm is the best. And for offline batch matching, that's probably the best website to visit before making this decision. But in production systems, there are various providers, including Quadrant. And really, if you want to share your specific use case, I would be happy to just have a call and discuss that. Just feel free to reach me out. I think that might be an interesting discussion, but that really depends on what you do.
That's very cool of you. All right, thanks, Girish, for the question.
Great, right? Jump right back into the community questions again. So this person asked, Nicholas asked in the community, this is a question from a while back, but I thought it'd be interesting to have here. And he says, working on rewriting the recommendation app, the app is heavily reliant on embeddings and very little on ML models. He's explored FIST and other feature stores, or he's kind of come to the conclusion that feature stores are not compatible with the app is building. He wants to know, how does the problem he's facing, is loading data from offline stores or streaming sources like Redis, for example, to the app itself. So it's kind of trying to figure out how can he successfully do that? How can he load data from offline storage to like a streaming platform in a maintainable way for his app? I don't know if that's fake or get there.
I'm not sure if that's really related to vector search itself, but I would say it's a problem that's, well, it used to be tackled with some ETLs back in the days. I'm not sure about this specific setup, how to move data to Redis. But unfortunately, this is not related to vector search, and I don't want to pretend that I know how to do that properly. I don't want to be really involved in a failure because of giving some piece of advice. So let me just skip that question.
Yeah, that's really okay. We'll definitely put this in check. And the next question for Paulo, do you have resources for duplicates detection or image similarity detection at scale? Like, for example, over 30 million images.
Well, that's quite a huge setup. Yeah, of course, if you work with duplicates, I would say perceptual hashing is also a great way of how to deal with that. But in terms of image similarity, then I'm not sure if that's a real issue to handle like 30 millions of vectors, because you eventually are not going to store all the images in any sort of vector search, but you are going to store the embeddings. But the question was about how to start doing that. So basically, you need to have a model. And for images, there are a lot of existing models like ResNets, which are quite commonly being used to create those embeddings. There is also a library that's gaining some popularity. It's called Embedder. And this is like wrapper around some existing embedding models with scikit-learn-like API. So this is pretty easy to be used. But I would also point to the article and demo that I created. This is basically about how to implement a visual search for e-commerce store that was done specifically on H&M dataset from Kaggle. This is available on our website, but basically there is an article describing the whole approach, how ResNet might be used in order to get those embeddings, and then finding the duplicates or some similar images is typically based on the distance from images. So the simplest approach is to use some kind of fixed threshold chosen experimentally. So you can just find those images which are similar by at least, let's say, 1.0.1 to the given query. But any kind of vector database should solve that, I would say.
Awesome. And that fixed threshold, is that use case dependent, or there's like a standard threshold that you figure out?
That's the simplest approach. I wouldn't say there is a standard threshold. Depending on which model you choose, that might be different. So that has to be chosen in some sort of experiment. So ideally, you should have data set with those images that you consider to be similar in some way. Maybe there is a case that I could share, because some of our users wanted to derive the similarity of the images based on the text that occur on those images. They were dealing with some book covers, if I recall that correctly. But basically the problem arises just because those neural models are not OCR systems, and they are not able to capture the similarity based on text that was written on those images, but instead they were capturing the visual properties of those images. So two images were similar because they were visually similar, not because the text was exactly the same. So that really requires having a specific data subset of your data on which you can just experiment and test it out to just estimate how wrong is your system. Because that might be, of course, estimated as with every other model that you can imagine.
Yeah, that's quite elaborate. Thank you for sharing that. Okay, another question. For vector similarity search, which of the tools do you recommend? The Facebook AI similarity search tool or the Milvus vector database? I know, of course, quadrants as well.
Sure, no worries. Yeah, definitely. Depending on the case you want to solve, let's say you want to have a quick experiment, perform this semantic search or neural search once, have some results, write a paper, and just forget about the whole project, then FAISS should be well enough, just because you are not going to serve those vectors in any production system. So there is no need to spin up a database, because FAISS will store everything in memory and there is no I/O operation included. But if you choose a vector database, you will typically need to communicate through an HTTP protocol or gRPC or GraphQL. So there will be some I/O overhead of sending those requests and receiving the response to the network. So FAISS would be way better if you just want to experiment quickly in a lab. But if you want to have a running system, then you need to choose proper vector database. Actually wrote an article on that. How is this vector library different to a vector database? And Milvus, in that case, that was the question. Milvus would be a better option if you want to serve that in any kind of running system. So vector database for production usage and vector library for some experiments.
Yeah, corresponds. And it's like you have an article for everything, which really speaks to the depth of your knowledge.
Well, some of those questions are those that I quite commonly get asked when participating in a kind of conference. So every time I have a new question that occurs quite often, I try to write an article summarizing those options, because, well, at the very beginning, I do not know the answer. But yeah, I think that would be quite well answering that particular question of when to choose which.
Right, that makes sense. Okay, jump right into the next community question. This person says they're working on deep learning based enterprise search products, and they want to understand how people make model updates to vectors in real time. And do you have a good learning resource for it, or maybe best practice? So their constraint here is that the vectors are stored somewhere from 1 million plus documents, and the system should not have any downtime. Basically, the processing should be in real time. The querying, sorry, should be in real time.
Yeah, got it. So basically, this is the question that I do not have an article for, but still, let me try to answer that. Yeah, that's a huge challenge. I think we already mentioned that, but basically, changing a model that is being used to create those embeddings requires lots of effort to switch all the running components, because in a typical application, you would have a model converting your data into those neural encodings. You would have vector database storing all those embeddings that you compare to. So you need to switch both at the same time. So every new request will be handled by a new model and will be accessing the new embeddings. So the process is quite tough, I need to say, if you have millions of vectors, because you need to pre-compute all the embeddings and store them. So this is not something that we do on their daily basis. This is a process that requires some experiments being done. So let's say we have a first model, we create those embeddings, put them into the vector database. And then after some time, we decide that we have a better model. So we do basically the same process again, but that takes a lot of time. That's a whole bottleneck of those systems. Unfortunately, there is no easy way. We need to compute those embeddings again, put them in the quadrant terminology. We would create a new collection and then just switch the collection in the runtime. So all the new requests coming from our users will be handled by a new model and by another collection in the system. That's one of the challenges that MLOps have to solve.
All right, looks like we're getting to the action part of the episode towards the end. Thank you for sharing that. And the next question here is, do you have some best practices for figuring out how well your embeddings work, especially for retrieval when you're doing vector search?
Yeah, of course, that might be measured just in a similar way like we do for some different models, depending on what problem we solve. But there are some metrics that's quite well described on Neptune blog. I have to admit, this is like the best source for the metrics description that I use and promote quite heavily. But basically, there are metrics like precision at K, recall at K, which are similar to those that we already know. There is an NDCG score, for example, or MRR. So there are some metrics that we quite commonly use in order to determine the quality and to compare some different models. So, well, the pipeline here is not that different to any different model. We have some validation and test data sets, and we calculate those metrics to then compare the results achieved by different models. So this is how it works. Depending on the use case, there might be some different metrics being used, but that's quite well described in terms of recommendations. If we perform some recommendations, we really care about some top results being shown to the user. And that's exactly the same process for some more question answering and all the other problems that we solve with vector search. But that's not that different, I would say.
Right. Basically, most of these actual metrics, normal metrics, standard metrics that people use stuff. Okay. Next question. What's the most effective way to test the end-to-end pipeline for vector search applications?
Well, if we just talk about the vector search, assuming that we have some embeddings, we are pretty sure about their quality. I would say we need to have some kind of estimate of how many. I'm not an expert in testing those whole architectures, I have to admit, but I would say if we have some estimates, how many requests we need to handle per second, minute, whatever, however we measure that. There are some standard tools of how to perform some load tests. But if we are talking about the quality, that's something we have already mentioned as well. I think we need to care about the performance, the time that is required to serve some results to the user, assuming a specific precision threshold or different metric threshold. So we have this guarantee that our results will be relevant for given query, not only that they will be provided as fast as possible.
Very nice. Thanks for sharing that. And what are the most common problems that teams run into when setting up MLOps for vector search apps?
It's still this changing the model, I would say, because that's the whole issue that arises from vector search. The need to recompute those embeddings and put them again. That may take lots of time. So definitely that's the biggest challenge of how to do it effectively. But as I already said, it's not something that we do every single day. That's a process that has to be planned, and there are lots of experiments included in order to change the model. If you have a model that you need to switch every single day, then probably something has failed during the training part. But that's the biggest challenge for MLOps. And honestly, I'm still looking for the best solution for that, but it's something that people really struggle with. Also remember one of the previous episodes of podcast with guys from Zero Alpha, I believe. That's also an issue that they mentioned. So I would say nothing has changed since June or July.
June. Yeah, thanks for sharing that. And I'm sort of curious because I want us to sort of deep dive into this vector search, tools, the database and stuff of it. And I'm thinking if I want to consider a vector search tool or a database, I have to think about my requirements, my criteria stuff before I start thinking about these things. And I'm curious, what in your opinion are the criteria I should critically consider before going out there and searching for a vector search tool?
Yeah. So first of all, you need to at least estimate how many vectors you may store in the tool that you will eventually choose. Because if you have like several thousands of vectors, then you don't really need to have a specific system to handle that. You can probably use a scikit-learn KNN with a perfect precision every single time, because this is not an approximate algorithm. But if you do that on scale, then you need to choose a proper tool. So I would say if you have hundreds of thousands of examples that you need to store, that's one of the things you need to care of. Those filtering capabilities. Let's say if you work with geolocation data, then that's a great addition to your vector database to have those bounding box or radius-based filters already built in, so you don't need to have a separate data source to then combine those results. But there are also many more. If you work with textual data, then some textual search capabilities already included are also great. I'm not really sure if things like distance functions are really important. I know that there are some systems that try to provide dozens of distance functions, but at the end of the day, everybody still uses dot product or cosine similarity, so it's not that important. If you want to do it in a production grade system, then you also need to know, at least estimate to some extent, how many requests you are going to handle, how many users may access the system in the same time. And if you know the number of vectors, a rough number of vectors you are going to store, then you could also think about how many machines will be required to handle this traffic effectively. Because That's definitely might be a bottleneck if you just want to provide this vector search capabilities for, I don't know, millions of users per hour, but you only want to run it on a single machine. So having a system that allows to spread the workload on the whole cluster is definitely a great choice.
Right. And we are definitely out of time, but I just wanted you to just maybe summarize this with this one last question. And that's that, what's, in your opinion, what's like one underutilized practice you see that people are not doing this enough when building vector search, when they are building vector search engines?
I would say that many people still try to use those pre-trained models without any further fine-tuning. So definitely fine-tuning the models in order to work better in your specific domain. I'm not talking about some big players that work with general knowledge, let's say, but if you work with medical data, then chances are that if you take ImageNet trained model, it won't work that well out of the box, but you can probably fine-tune it quite easily, so it will provide you with some better results. So fine-tuning to the rescue.
Awesome. That's all for me. Sabine?
All right. Kacper, thank you so much for coming on to share your knowledge and practical tips.
Thanks for having me. That was a real pleasure.
For sure. So you very helpfully offered to assist people and talk more about some things. So how can people get in touch with you and follow what you're doing?
I would say LinkedIn or Twitter are the best ways to contact me. I'm quite active, and as a developer advocate, that's part of my role to help people to sort things out. So definitely feel free to reach me out with anything related to vector search, but not only.
Awesome. Thanks. So here at MLOps Live, we'll be back in 2 weeks. And next time we'll have with us Jason Flex, and we'll be talking about deploying conversational AI products to production. So in the meantime, see you on socials and in the MLOps community Slack. Happy holidays. Take care. Thanks, everyone. See you. MLOps Live is brought to you by Neptune.ai. Remember that you can join us live at the next event and ask your questions. And you can register at neptune.ai/events.
And then make sure to search for MLOps Live in Apple Podcasts, Spotify, Google Podcasts, and anywhere you get your podcast. Click follow and don't miss any episodes.
Thanks, and see you next time.